Today under crystal field theory, we will be looking at crystal field splitting in a tetrahedral complex. Now generally tetrahedral complex are of the type Ml4. Few of the examples are cobalt Cl4 2- and NiCO4. So these are a few of the very few popular examples of a tetrahedral complex. Now whenever we see the structure of the tetrahedral geometry, then this is our central metal ion, and the black colors are the ligands, that is the four ligands that are oriented along the corners of the cube, that is they are oriented in the two opposite corners, two on the top and two opposite side on the bottom. And the axis, that is these are the axis, suppose this is z axis, this will be x axis, and suppose this is the y axis. So these are the axis. Now when we look at the orbitals, then in case of the orbitals, suppose if we are looking at x square minus y square, then this will be our x square minus y square. And this orbitals, basically we can see that the dx square minus y square and dz square, this orbitals, they are touching the center of the cube. This will be dz square. So these are touching the center of the cube, that is the center point of the faces of the cube. Whereas when we see the orbitals that are present between the axis, say suppose if we draw d xz, then this dxz will touch this corner, that is over here, whereas similarly dyx will touch this corner, similarly dxy will touch this corner, and so on. So in tetrahedral geometry, this incoming ligands, they are neither coming from the axis nor they are coming from the plane, but they are coming in between. And when we measure the distance, that is the distance of the orbitals, so for dxy, dyz and dzx, the distance will be l by 2. Suppose this is l is the length of the cube, so distance will be l by 2. And if we look into the center, that is if we are looking at the center point of the cube, that is this diagonal distance to the center of the cube over here, wherein the orbitals or the face of the orbitals lies, then this distance will be L under root 2 by. So this diagonal distance L under root 2 by 2 is greater as compared to L by 2, and as a result the orbitals, that is dxy, dyz and dxz, these orbitals are closer to the ligands as compared to the axial orbital, and as a result the electrons of dxy, dyz and dzx will experience more repulsion as compared to dx square minus y square and dz square. As we have seen earlier, initially all the 5 d orbitals, they are degenerate, they are having same energy. Now as the ligands come closer, they will form a uniformly distributed spherical structure, and this is our average energy state, or it is also known as the barycenter. Now the splitting will take place with respect to barycenter, wherein the ligands will orient themselves in such a way in order to minimize the repulsion. And over here, as the distance of the ligands from dxy, dyz and dzx orbitals are closer as compared to the other orbitals, the 5d orbitals will again split into the set of 3 orbitals and the set of 2 orbitals. Now this set of 3 orbitals is represented by T2, and the set of 2 orbitals, it is represented by E. Over here the tetrahedral complex, it does not have center of inversion, and as a result we are not talking about whether it is Girard or ungirard. And this is the center, that is the barycenter. Now with respect to barycenter, the difference of energy, we could write it as either 2 by 5t and 3 by 5t, or the complete energy difference we are writing it as delta t, and this will be 0.4 4 delta T, and the lower will be 0.6 delta T. In many books it is written positive, in many books it is written negative. So negative, it represents the decrease in the energy, in turn reducing the stability of the molecule, as the ligands, they are neither coming from the axis nor they are coming from between the plane. The magnitude of splitting will be lesser as compared to the octahedral complex, irrespective of the ligand, whether the ligands are strong field ligands like C and CO, or whether they are weak field ligands like Cl minus and F minus. The magnitude of splitting will be smaller, and the difference between the octahedral and tetrahedral is that tetrahedral is 4 by 9 times the octahedral, and this 4 by 9 times it is because the tetrahedral has 2 by 3 times less ligands, and as a result, and as the ligands are not directly approaching from the axis, the repulsion between the ligands is 2.2 by 3 times lesser, and hence it is 4 by 9 times delta O. That is 4 by 9 times the magnitude of splitting, tetrahedral splitting, is 4 by 9 times lesser as compared to the octahedral complex. So this is how the splitting of tetrahedral complex takes place.